Hi, my name is Angela Harney. I'm a Snowflake data superhero. I work at Unify Consulting as a senior consultant in data engineering and cloud services. I'm here tonight with the Snowflake Seattle User Group and my co-chapter leads, uh, Krithika Balaji and Richard McHenry. We are welcoming our partner spotlight tonight, which is Espresso.AI. And here with us is Ben Lerner, the CEO of Espresso, to give us a technical presentation on everything that it's about. Our focus is performance, cost optimization, AI, machine learning. So I'm going to hand it over to Ben to show us the um, great benefits that I've already seen and heard of from Espresso AI. So thanks for being here tonight.
Uh, Thank you very much for having me, Angela. Thanks for the warm welcome. Yeah, I'm going to be going through a bunch of technical content, just kind of explaining what does Espresso do under the hood. We have a pretty small group in person, so feel free to ask questions. I think presentations are more fun when they're interactive, and part of the benefit of coming to something like this instead of watching a YouTube video is that you can, pause and say, "Oh, hey, that doesn't make sense," or "Oh, how does that work in a little bit more detail?" Anything like that. Um, yeah. Uh, but to kick things off, so we're going to talk about AI for Snowflake cost optimization. Hold on. Okay, my
Okay.
fancy clicker is working. Um, so I'm Ben. I'm one of the co-founders of Espresso.AI. I'm also the CEO. We've been around for about 2 years. Uh, we use machine learning to automatically optimize Snowflake. Um, and before this, I used to work on performance engineering and machine learning at Google. So I have a background in a couple different things. The immediate preceding thing was high performance systems optimization in Google Storage, rolling up into Google Cloud. Um, if you're on Gmail or you watch YouTube, somewhere very deep in there is my code shuffling some bits around. And my co-founders and I all worked together before that on Google Search doing natural language processing. So, what does ML optimization look like? Like, what does this actually mean? Um, we make Espresso as a system makes a bunch of real-time decisions around how to run your workloads to minimize cost without impacting latency. Um, it's similar to Borg or Kubernetes. Uh, do you folks are you familiar with Kubernetes? Is
Not
anyone
directly.
not familiar? Okay. So Kubernetes is kind of the modern way that data centers are run. It's a little bit different from how Snowflake is run today. So when you set up Snowflake today, what you typically do is you statically map different workloads to different warehouses. So you might have a BI warehouse, DBT warehouse, and another warehouse for people typing things into Snowsite. Um, some orgs that we've seen do this differently, where they'll split it up by department. So they might have a finance warehouse and an analytics warehouse, and so on. And then everything just statically is assigned to the same cluster. Uh, it turns out that this is pretty inefficient at scale because you always have a different set of workloads that are running. And what you really want to do when a query comes in is not say, okay, well, you know, Angela wrote this query, so this should run on Angela's cluster. What you want to be able to say is, well, what else is up and running? What machines do I already have up that I'm paying for? And can I route this to one of them with capacity? Um, this is the idea behind what at Google is called Borg. So this is sort of the nervous system that runs a data center where every job that runs gets sent to a scheduling service. That scheduler looks at what is all the different hardware that is up and available and running? So, and where can I slot this in to optimize costs without impacting performance? Um, Mapping that back to Snowflake, that's what Espresso does under the hood, or that's a big part of what we do today. We will take workloads as they come in and we'll say, okay, well, this was going to go to an extra small warehouse, but you have an idle small warehouse that you're already paying for. So we're going to run it there. Or you have two large warehouses running. They're not at capacity. You don't really need to spin up a third large warehouse. You can just run it on one of the first two.
And the reason it was the small was still running is because it might have been in its less than a minute was when a query executed and there's still 50 seconds left, or it's on a suspend of, a 5 minute suspend timeout burn down,
Yeah,
correct? Yeah.
exactly. So it might be that it's in a 60-second suspend. It might be that we know that this was going to take 10 seconds on an extra small, and maybe there's a small that's about to have capacity. So it makes more sense to run it on the small, even if it has to queue for a second or two.
Mm,
Um, there's also just there's kind of scaling in time, right? So there's this idea of a warehouse is idle or not, and that's kind of the way Snowflake presents their metrics.
mm,
But at the same time, each warehouse is many physical machines. Well, an extra small is one machine. Each machine has a bunch of cores,
mm,
and so
mm,
stuff can also run in parallel. And if you're looking at something like a large, which is you know,
mm,
32 machines, something like that. Um, you can often just, they're probably not all fully utilized. So you can
mm,
often find a few cores that are available, especially for running smaller queries. The other thing that comes up is BI workloads, right? So if you have a BI workload where there's a user interacting with a dashboard, there's just going to be gaps in between different queries as they go back and forth, and you can start to kind of fill in those gaps with some other
mm,
queries.
Cool. Thanks.
Yep. Um, when this is running in practice, our system makes thousands of scaling and routing decisions each day. So every query that comes through, we're trying to figure out, is there somewhere better we can run this? If you're on multi-cluster scaling, we'll constantly kind of be monitoring, do you have the appropriate number of clusters up? Uh, One thing to note in terms of the scheme, the kind of greater scheme of cost optimization, um, we are business logic agnostic. So something that I always say to customers who are in the process of cost optimization is you should still go talk to the different, you should figure out what your top workloads are and you should go talk to the people who are running them. If someone is running a dashboard that's costing $100,000 a month, we might be able to get that to cost 50, but if that dashboard shouldn't be running, you should just turn it off.
Mm, mhm.
So what do we do under the hood? Oh, no, sorry, this was the joke. How does it work? It works really well. Um, Normally, when I present this in person, I have the next slide thing off to the side, which
Mhm,
is really helpful for my comedic timing.
mhm,
So I apologize in advance for however many other jokes I'm going to whiff.
mm,
Um, when you start working with us, we can take a snapshot of your metadata for the past few weeks. We can train up some models, and we can actually estimate what is your bill going to look like if you start working with us. Um, this is lightly anonymized data, but the percentage savings are real. So this is a real user, a real Snowflake user that we talked to that later became a customer where we ended up saving them three-quarters of their bill.
It's oh, when you said you went in and grabbed their information, did you go in and kind of look at like query history? You need to get in and log in to their account. There's not some way that they can extract and export query history to you, is that correct?
Uh, Great question. So there's a couple different ways that this data can be shared. The easiest thing is to just run our onboarding process, because then the benefit is we can also flip on as soon as you're happy with the numbers.
Mhm.
But you can also just upload the data to us directly. So
Oh,
um, if you'd prefer not to create an account, and that is a common ask that people have for security reasons,
mhm.
we can, if you log into our dashboard, you'll just get a Python script and you'll see what exactly are we uploading. That gets sent straight to S3.
Mm.
Um, we're also happy to sign an NDA.
Mhm.
Yeah, and
Okay.
in general, we're also happy to do security reviews and all of that stuff.
Yeah, upload to an S3 bucket's a great option. So thanks.
Yeah. Um, okay. Uh, so how does it actually work? Um, Step one is our infrastructure. Uh, this is a architecture diagram that we share with people. The short answer is that it works over a proxy. So there's a proxy that sits between your tools and your data warehouse. Um, and you route your queries to the proxy. In practice, the way that you set this up is for your tooling, you just change your connection string from your account.snowflakecomputing.com to your account.espressocomputing.com. So this takes a couple minutes per tool. It's something that we're happy to walk you through.
Mm.
And in the case of Snowsite queries, we can give you a Chrome extension that will do that for you transparently in the background. Um, Proxying things lets us rewrite which warehouse things are running on. It lets us rewrite the queries to make them more efficient as well. The second part is an agent that monitors your warehouses. So this is the onboarding process that I mentioned where you create an account for us. Um, we will sit and kind of every few seconds monitor the state of everything that's running. This is how we make scaling decisions in terms of cluster count. This is also very helpful to make scheduling decisions, especially in the case where we don't fully see every single query running through the system, which is really common. So this kind of completes the reinforcement learning loop of getting feedback back from the environment to understand what is going on. Um, the second part is literally like copy paste a script to create a user account for us. So modulo security reviews. That takes usually a few minutes. And that also by itself can start netting you about half the savings that we typically see. Um, the reason we do a savings estimate is there's a wide range with how effective this is. We've had customers where we save 80%, we've had customers where we save more like 15%. But typically, for a larger user that's on an enterprise plan and doing a bunch of multi-cluster stuff, just the agent will typically get you to 25% savings or so, and the proxy usually ends up closer to 40.
And then on that, quick question on that user
Mhm.
account, does that go into like what role? Like account admin, security, you know what I mean? Uh,
Yeah.
sysadmin?
So we create a custom role and we try to really have the minimal number of permissions. So it just ends up being like Espresso.AI role or whatever naming convention. Um, One thing to note is we don't, through that role, have any access to any of your data. So
Mm.
we can see your query history. That's
Mhm.
the most sensitive thing we can see. Everything else is, basically machine metadata. So warehouse event logs,
Mm.
billing history, stuff like that.
Mhm.
Um, the proxy like has data in transit, but that's never written out to storage anywhere. That only sits in memory. It's never logged. It's never looked at. So this entire system um, has no access to your data. Cannot make queries on your behalf. Um, One of the things that my team and I learned in Google Storage and Google Search is how to really make something that's very secure and not intrusive. So this is meant to be as far removed as possible from what you're actually doing while still being able to optimize it.
And when you said it goes into memory, does it go into Snowflake memory? And so nothing leaves, outside of its encryption and security system, correct?
Um, yeah, so it by memory I mean like RAM on the proxy. So the only piece of our infrastructure that it touches is the proxy. And also, that is a really simple process that
Mhm.
enterprise users are welcome to self-host. That's an option that
Mm.
certainly when we talk to banks, that's something that banks have been interested in.
Okay, thanks.
Um, Question. So this could be
Yeah.
you part, this could be you
Yes.
box. I would assume that can also be an ETL tool, for instance.
Mhm.
And
Yeah.
then part two of that question would be, so how do you handle sort of the things that are now happening internally in Snowflake, like streams and tasks, dynamic tables, things of that nature that are all happening within the environment? How do you get your metadata on that?
Yeah. So for the stuff that we can monitor, the data that we get back out is so actually, I guess there's a couple ways to answer that question. One is just the query history table. So we're going to see what you're looking at and what you're running. And then for real-time decision making, we are looking at specifically what's running on your warehouses. So we get a readout of that basically by just calling show warehouses.
Mm-hmm.
Um, Anything else, just like we sort of will just forward the request. So even if you're using some more advanced features, we can sit in the middle there and kind of intermediate and think about, well, should we do anything with this request? Should we, if it is running on a cluster, should we run on a different cluster? If it's a SQL query, should we write the SQL query? If you have, you're executing Python or something, at least for today, we're not going to touch it and we'll just kind of pass it on. Although again, we may say, hey, there's capacity to run this somewhere else, and that's what we're going to do.
Mm.
Cool. Okay. So once the info's set up, what are we actually doing to get improvements? So I'm going to talk about a few different things: query optimization, online scheduling, offline scheduling. Um, Query incrementalization is another fun thing we're doing that's not actually AI based, but if we have time, I'll talk about that too. Um, okay. So how does query optimization work? Um, does anyone know how ChatGPT was trained?
No, I know it's built with Streamlit, but um, mm,
Um, so ChatGPT was trained through a process called RLHF, which stands for Reinforcement Learning from Human Feedback. And the basic idea for RLHF is you start out with one of these giant LLMs, and then you run a process to fine tune it to get it to actually do what you want. Um, Human feedback in this case means they literally would prompt the system with the sorts of things you might put into ChatGPT, and then ChatGPT would give a couple answers, and you would, they had humans sitting there going, well, I like A or I like B. And eventually, over time, the system learns to move towards the things that people like. Um, it turns out that getting humans to do this is very slow and expensive. So eventually they actually train another model to be able to guess which of two answers a person would like. And then they largely just use that to train the bigger model.
mm,
Um, that's basically what we do. So we have a large model. Um, we have a different model called a cost model to kind of align with standard ML terminology. So we have a cost model where you can give it a query and it'll tell you, I think this is going to take 2 seconds to run, or I think this is going to take 8 hours to run. Um, and it's kind of important to know which of those two it is. Uh, we outside of machine learning, we use formal verification to prove correctness. So one important thing about automatically optimizing queries is that you want the output to still give you back the same answer, right? The problem with plugging something like ChatGPT or Cortex directly into this is it is going to hallucinate from time to time,
Mm.
both sometimes making your query slower because it doesn't actually know what's fast and what's slow, but also just sometimes giving you back the wrong query and giving you back the wrong result.
Mm.
Um, Oh, one thing I should mention about the cost model is we're working on integrating into our Chrome extension so that you can know in advance how long a query is going to take to run. Not only generally, but also based on like which size warehouse you want to run it on. This is something a bunch of customers have asked us about, so I'm
Oh
kind of
yeah.
excited to get that out there. I think it'll be fun.
I'll give you an extra dollar for that. That's excellent.
We're going
Mm.
back and forth on if we need to charge for this.
Mm.
One of the benefits of being VC funded is, we can just try it and see, and if it ends up being extremely expensive, then
Mm.
we'll uh,
Mm.
put in a credit card form. But it should be fun. We've had a bunch of people ask, and our models are getting to the point where we think we can just support that, which I think will be good. Yeah, so we have a cost model that's going to tell you how long things are going to take to run. We have a system that can check if two things are the same. Um, and so then we reinforcement learn the bigger language model to output fast, correct queries. Super, super straightforward, right? Basically trivial. Uh, okay. Um, for people in the audience who are currently doing CS classes, um, a common concern that people taking an algo class have about number two is that this is impossible, which is a reasonable concern. And while it's not possible to prove that any two, like to prove whether any two queries are equivalent, you can certainly sometimes prove that two queries are the same. And it turns out that you can do it enough of the time to do interesting, efficient optimizations. Yeah, I kind of talked through this, but an optimizer that hallucinates is not very helpful. Testing doesn't work here either. Some people assume that we do something like run the optimized query, and if it gets the same answer as the slow query, then everything's great. Um, this doesn't work, and here's a really simple example. Um, I can write two extremely different queries that are both going to return no results. And just because two queries return no results doesn't mean that they're always going to return no results or that they're always going to return the same result under the same circumstance. There's more complicated versions of that where, by the same token, like summing a column might be the same, and then eventually, like two more complicated queries can diverge.
Yeah, one record set might return 1 million, and one the next time with a different value might return 10 rows. So,
Exactly. I mean, even just the same query with limit 10 and limit 100 is going to do the same thing for a while, and then they'll do different things.
mhm.
Yeah, uh, we don't need to do the halting problem. Um, this also works well. It works better than you would guess, I would say, because of reinforcement learning. So reinforcement learning is essentially a way to train a model to do whatever you want, if you can get it to converge and if you have enough of a GPU budget. So to some extent, the model learns what sorts of things the formal verifier understands, and then it can pick optimizations that are going to get past the correctness check. Um, this is a technical point, but if you uh, one way to uh, say that two things are wrong is, just give back a bool, right? Like, yes, these are the same. No, they aren't. A different, more helpful thing to do would be to put a metric on the verifier. So say, hey, these queries are almost correct, or these queries are almost the same, but not quite. Um, if you know how to do that, you should email me.
Mhm.
Okay. Why are we doing reinforcement learning? So traditional machine learning, uh, or more normal machine learning, or whatever you want to call it, is more commonly something called supervised learning. So you have a bunch of data, you have a data set, and you have a bunch of things that are labeled, right? So if you want to train a handwriting classifier, you get a bunch of labeled sets of what different letters look like. If you want to train a image classifier to identify when cats have photos in them. You have a bunch of photos with cats, a bunch of photos without cats, and you feed the two different things into the classifier, and it'll eventually learn to pick this up. Um, in terms of query optimization, there aren't really great data sets of, hey, here's a slow query, here's a faster version of the same query. There are some, but there aren't the you know, trillions of tokens worth of examples that you would want for an LLM. Um, The other nice thing is reinforcement learning can learn weirder stuff effectively. So Snowflake SQL is not exactly the same thing as every other variant of SQL. This can even pick up on things like, oh, this workload, scales differently on a large machine. This workload scales differently as the machines get larger, or
Mhm.
this thing runs 20% faster on Gen 2, whereas this one only runs, 10% faster on Gen 2. This one runs 50% faster. So here's, if you're optimizing for cost, how you know when to flip over to that warehouse. Oh, yeah, it's like Snowflake sort of doesn't have indexes, right?
Right.
Indexes are normally very important for tuning. Snowflake has uh, pruning, which is, you know, similar but different. Um, in practice, starting out with a bunch of examples is probably helpful. Um, Prompting ChatGPT or Claude or something to generate a bunch of examples for you may be helpful, but reinforcement learning is actually really helpful here.
So you probably do well with a little bit more history in your performance optimizations than someone who only maybe has a few weeks of history, correct?
Yeah, there is definitely diminishing returns to more and more data. At this point, we have a lot. Um, Interestingly enough, uh, this is a little bit of a tangent, but one of the odd things that VCs get a little bit wrong about investing in machine learning companies is um, because of the way social networks work, like investing in network effects is a very good thesis, right? If you're Facebook,
Mhm.
it's really hard to dislodge Facebook because everyone's already on Facebook.
Mhm.
Um, Machine learning absolutely doesn't work in the same way because you basically need an order of magnitude more data to get an incrementally better product.
Mhm.
So we might have, 10 times more data than a new company, and some of our more established competitors might have 10 times or 100 times more data than we do, but that really is kind of marginal. But yeah, having more than a week is really helpful, and
Mhm.
looking at a few months of history per customer is also extremely helpful.
Great.
Um, yeah, cost model works well. The cost model actually enables the scheduling stuff, which we'll talk about. And one of the nice things about the cost model is there's just less pressure on correctness, right? So if we're rewriting the query, it really, really needs to be correct. If I think a query is going to run in 2 minutes and it actually runs in 130 seconds, that's, worse than being wrong, but the error is pretty bounded. So it's a good place to start. Um, Here's an example of the sort of thing we do. This is the query on our homepage. Um, one interesting thing to note is that this is not real SQL that will compile because we took out some quotes and stuff to make it fit onto the screen. But it's pretty obvious what the actual SQL is. So this is the rewrite, and we can go back and forth here. So basically, there's an extra join in there that just came out of some templated ORM stuff in somewhere in Tableau, almost certainly. And other than rewriting it to look more sane and human, it figured out that you don't actually need that join. Uh, you can just drop it um, based on the schemas of the tables involved. And then as a result, this runs twice as fast. Uh, it turns out one of the things that our model is good at is like ungarbaging ORM templates. That's something that humans find difficult to reason about. And I think because humans find difficult to reason about it, compilers also find it difficult to kind of power through because all of the compilers were written by humans, at least for now.
And that is the one thing that you can do to make Snowflake um, cost less is to make your queries efficient. Bring less data, like you say, to scan by removing a join, denormalizing your data so you just bring less data to the equation. So I think that's awesome to see that you can rewrite a join out of there. That's cool.
Thank you.
Mhm.
Um, any questions so far? I'm just going to be pausing a lot. No. Every single thing made total sense.
I'm asking my questions along the way. So
All right.
mhm.
Cool. Well, sounds like I nailed it.
Mm.
Okay. Online scheduling. Oh, okay. One of the people taking classes, what's the difference between online scheduling and offline scheduling? No, no one took an algo class.
Uh,
Okay.
uh,
So online algorithms and offline algorithms are different in the following ways. An offline algorithm is something where you have all of the data up front, and you are making whatever decision you need with all of the data. So, for example, if you have a list of data and you need to find the median, the offline algorithm is fairly straightforward. Um, I mean, there's more efficient ways to do this. So the inefficient way is to sort all the data and pick the thing in the middle. There's a way you can do it in linear time. But either way, uh, online scheduling is algorithms that you do live, so hence the term online. And in that example, that turns into something called the streaming median problem, which is actually a lot harder to do because you
Can you
don't
repeat
know
the
when you're going
problem's
to.
name?
Oh yeah, the streaming medians. That's a lot harder because you are like you don't know what you're going to get. You don't know where in the list you are. You don't know how many more pieces of data you're going to get. And any piece of data may be the correct answer eventually. So if you don't relax the constraints, you have to store a ton of data, which is not always practical. Um, so yeah, online algorithms can be a lot harder. Anyway, so right. Uh, it turns out that you can do a lot better than static scheduling, especially if you know how long things are going to take to run, how they're going to scale, and how they're going to parallelize. So if they're going to queue or not when you run them on existing warehouses. Um, if you want to read a paper on org scheduling, that's the paper. So I don't remember if I said this earlier. Um, this is basically the Kubernetes scheduler. For Kubernetes, you would label each job with the resource requirements. So you would say, this needs 300 megabytes of RAM and, this much bandwidth and a quarter of a CPU. whatever. Um, Obviously, Snowflake queries don't come in with anything like that, and so our models are effectively taking the place of hand annotations, and that's kind of how we know, yeah, this query was going to go run on Angela's warehouse, but actually we have capacity over here, and that's how we know it passed, like this is idle or not. So here's kind of an example of what it looks like. You have a DBT warehouse, you have a Looker warehouse, and you have some ad hoc queries coming in. In total, you're spending 3 credits. And if you just stick them all in a medium warehouse, everything runs in the same amount of time, and you can save 50% on credits. Um, One of the assumptions here is that maybe you're not benefiting from the large warehouse with the DBT query, for example. Um, Fairly common, especially because people have a tendency to Peter Principle their warehouses. They'll just keep sizing them up until they don't get any more return, and then sometimes you end up with one size too big. Um, okay, this is a simple example. Uh, this is what it actually looks like. So this is a trace over, I want to say 24 hours. It also could have been 8 hours. But basically, on the left-hand side is for this particular run with a beta user, the different warehouses that they started out on, and all of these black bars over here are just different warehouse names that I removed from the example. And then over on the right is where these things actually ran. Um, we ended up saving something like 30-40% here. And you can kind of see like what normally was this big chunk of work on this warehouse, which was driving a lot of the cost, now gets split amongst a lot of other warehouses because you can sort of fit a bunch of it into idle time on these other machines. And that's basically where the savings come from.
Nice.
Okay. So we went over this a little bit before, but in more detail, what is the machine learning actually doing, right? So we're predicting a bunch of different things. Um, Pre-processing time. If we know that something is going to take 45 seconds to compile, that can actually sometimes really drive costs. So it's helpful for us to know kind of how to queue things in time, not just in space. Um, Runtime, obviously. Uh, they will, knowing how long things are going to take lets us know, when do we put things where? Is this, if this is going to run for an hour and it's going to fully utilize the machine, we don't actually really need to worry about it. But if it's going to run for 3 seconds, maybe you don't want to pay for 60 seconds of compute. Um, the query incrementalization is because the slide is in a different order from when I first wrote it. So this is now a reference to something I haven't talked about yet. Um, Scaling and concurrency. So this really lets us get more out of the hardware that you're already running, whether it's because you sized up too much or because you're actually running on a size that's too small and you're spilling out to disk or to remote disk and kind of burning a lot of time waiting for networks calls. Um, and again, if you have, a warehouse that's running 5 queries but could be running 7, that's also really helpful to understand. Okay. Um, Questions on that stuff?
I think I'll have some questions after you describe offline, the difference kind of between the two. But
Yeah, um, they're quite different, is the short answer.
mhm.
Okay, so offline scheduling is something we are working on specifically for DBT. Um, it's not DBT specific in the sense that you can apply offline scheduling anywhere where you know what queries you're going to be running in advance. But the integration is kind of per tool specific because you need to be able to get that data somehow. Um, We do have aspirations to just automatically pull that data out of your logs. And, if you're running the same job every day, maybe we can sort of guess that this is the same job moving forward, is the same dashboard. But it's really nice to just be able to pull that out as a file and not have to piece it back together. Um, so dbt is the most popular tool used across our customers. That's why we have some dbt specific optimizations that we're working on. Um, and yeah, like you can do this anywhere you want if you're so inclined. Um, so again, this works over a proxy, right? You stick us between dbt and Snowflake. In this case, for this integration, there's some dbt specific stuff where you set up an account for us there so we can actually read the query plan. Uh, Forget what they call the query plan, but it's not like a Snowflake query plan. It's like the plan of all the queries they're going to run. So yeah, dbt jobs produce a DAG of queries for your ETL job or your ELT job. A DAG is a directed acyclic graph, so it's just, this is going to run, then this is going to run, then this is going to run. Maybe these things run in parallel. Um, there are lots of ways to execute most DAGs. That's kind of the core part of that's the core thing to understand for offline scheduling, right? You can run these things in different orders. Um, we did a bunch of scheduling theory work to find faster execution plans. This was really cool because there was someone in the office doing actual graph theory. It wasn't me, but it was still nice to be aware that math was happening. So this is an example DAG that we pulled from a customer. This is, believe it or not, actually a pretty small job, and it's not even a screenshot of the full thing. So, this starts getting into a good bit of number crunching to be able to do anything useful. So here's a little bit of a simpler example, right? 6 queries, assume that each one takes a minute. And if you run them on, like by default, Snowflake will just run it on one warehouse. They'll do it all in series and it'll take 6 minutes. Um, what you can do instead is actually look at the structure of the DAG and run more stuff in parallel. So you can run the first 4 things that don't have any dependencies on 4 different clusters, and then uh, CNF, the only things that actually do have dependencies, can run on, I mean, any of these clusters, but um, I stuck them on 3 for this example. Uh, and then you can run everything in 3 minutes on 4 different clusters. Um, Same runtime in this case. It's not any cheaper, but it is faster. And one is Snowflake already has a way to trade off time for speed if you want. So you could potentially size these down, which is a little bit more efficient most of the time. Um, and then 2 is obviously this is like a really simplified example. So you can also do things like run some things on larger warehouses, some things on smaller warehouses, or some things on Gen 2, some things on Gen 1, and start, if you have an SLA to hit, or if you're just trying to make sure nothing is running slower, you can start figuring out, where do I actually pay for performance and where do I not need to pay for performance? Where can I let things run and it's not going to impact how long the job is going to take? Um, Really, the best way to do this is a bunch of graph theory. So here are some papers about uh, this is a variant of bin packing. Um, and yeah, there's like almost an unlimited number of really technical theoretical papers you can read on this topic, some of which have good results. And these are some of the classic ones. Um, oh, yeah, we saw like 30% or so speedups with some beta tests. So it's significant. It can be comparable to running everything on a larger warehouse for free, or running everything on Gen 2 for free. Okay, questions there?
I do. And now, so do you have a certain set of warehouses that folks kind of set up and say, hey, use this set, don't use these, with preferences for
Yeah,
offline or on. Yeah.
yeah. That's a great question. So we do, or we can support that. Here's why usually you don't want to do that. Uh, so part of the whole idea of using something like Borg or Kubernetes is a separation between logical and physical compute. And this is the idea that logically there are lots of ways to group your workloads, right? You may want to group them by which warehouse they run on, which is how most, or sorry, you may want to group them by which tool they're coming out of, which is how most people set up their warehouses. You may want to group them by user or by department or something for quota purposes. You can use tags to do all of this. What you don't want to do is pay 30% more, 50% more to something that you could do for free with tags. And so that's kind of the physical compute aspect of it, right? When you're actually executing some work, ideally you just want to run it on whichever machine is cheapest. Um, and under the hood, like all of this is running on AWS anyway. Snowflake can spin up pretty much any machine anywhere in a data center it wants. You don't actually get a whole lot of information. So we can report back because so many people use warehouses for cost management and reporting. We can map back to, hey, here are the warehouses that, here's the cost breakdown based on the original warehouses you sent this to. It's almost like, you know, transforming the warehouses into effectively tags. But yeah, generally we encourage people to say, hey, just let us pool all of your compute. That said, people do have different requirements about this, whether they're departmental. Sometimes people have legal requirements that we can't run this workload with this other workload. So we
Mhm.
definitely can create these pools. And the bigger the pools are, like having two pools that are roughly the same size at scale is probably fine. If you start having 17 different sets of warehouses that can't
Mhm.
be commingled in ways, then um, you're probably leaving a bunch of money on the table. And then there's a question of, is there someone you can talk to about why you have this policy and what they think it's accomplishing in a way that, if you're really just using it to tag the data, there's just better ways to do that.
Mm. And one of the things that it almost is a request, if something like this is possible. What would be really cool is if there was that concept where you're able to say, hey, this query is about to take 20 minutes or something like that. And if you were able to direct it to, hey, this particular resource over here, can you direct to traffic specifically like that?
Yeah, we totally can. Like, are you want to direct long-running queries to a specific warehouse?
Yes, because the resource monitor on there may be set up to take a certain action on ones that are,
Oh, interesting.
yeah, like stop it or, suspend differently.
Uh, yeah, that's really easy.
Cool.
We could talk more about that.
Hmm.
We are trying to decide what sort of interface is good to have here. The other kind
Hmm.
of related thing that we've been talking about is what should we do if you're sending a query to a warehouse where it's going to time out? If you have
Hmm.
a 20-minute timeout and we think that this thing is going to run for 6 hours,
Hmm.
like we probably ought to do something.
Yeah,
And
yeah.
it's silly to just run it and let it cancel. We
Mm.
have an active debate going back and forth whether we should just error it out right away, and if that's going to
Mhm.
be frustrating for people, or if we should send you a message and basically you have 20 minutes to see that message in Slack and say, oh yeah, like up it to 6 hours or just cancel it right away. Um, if it's in Snowsite, it's very easy to pop something up and just say, hey, this just isn't going to work. But if you have a, you know, I mean, certainly what you don't want is to burn a bunch of compute to have the job crash. Um, so that's something that we're thinking about.
And I know these are
Unrel-
outliers. Yeah, but in your
yeah,
off, sorry, so in your offline schedule, so if you've got, DAGs or a set of jobs, run, every day or at a certain frequency, and you know that this one always runs and takes an hour when it runs. If you see, hey, this time it's going to execute and it's going to go X factor up above that 1 hour, alert or take action or something like that, or send to warehouse, etc.
yeah, that's a good idea.
Yeah.
Um, the other thing I was going to say is this is not very ML. This has nothing to do with ML, but just retrying failed queries seems like it would be helpful. Sometimes they're just intermittent job failures, and
Oh,
one of the um, very commonly when people turn us on, we turn into kind of first line tech support for Snowflake because from
okay.
that moment on,
Yeah.
anything that ever crashes in Snowflake, the first thing people ask is, "Did you do this?"
Uh,
Um, and that's fine. We're happy to work with people, and I'm exaggerating a bit.
mm-hmm.
Eventually,
No, because there are,
it settles
a lot,
down.
a number of times it is because the AWS node gets overwhelmed or something like that. You know what I mean?
Yeah,
So,
yeah. And so, for anything that's flaky at all, the reasonable thing to do is retry it. And so we are talking about, hey, do we just enable this in, transparently in kind of jobs where we know there's some frequency of flaking so that someone doesn't have to go manually rerun it. Um,
mm-hmm.
but we need to get permission from people to, I think, burn more credits for that and make sure that's what they
Right,
want.
right. If it's maybe certain, AWS errors where, hey, right now this, was a um, spot that was just kind of overwhelmed or hit a certain uh,
Yeah,
contingency that, yeah, those should the user that sent it in isn't going to know that's what happened, and they're going to be spinning their wheels at trying to
yeah,
resolve something. So,
yeah, exactly. One thing to mention about online versus offline scheduling is it's not actually even entirely obvious that this is the same problem. You use very different techniques, and theoretically, offline scheduling is more powerful, right? If you know everything in advance, you can make better decisions. Um, in practice, the reason online scheduling is important is because workloads at any sizable place, there's so many workloads running in parallel at any time, and there's so much randomization that you're never really going to see the same set of things going at the same time. And so being able to make these decisions on the fly, maybe with a little bit of predictability of what you think is coming down the pipe, is more effective than doing a bunch of offline planning. But they're both fun and they both work well in parallel. Okay.
yeah, awesome.
Um, Query incrementalization is one last thing that we're working on. This is just a little good old-fashioned compiler work. It's not ML based, but it's something that we've seen can speed things up a lot. So you can run ELT a lot faster through incrementalization. If you're not familiar with incrementalization, that means so the easiest way to load data is to just rewrite the entire data from the source. And it is obviously much cheaper and easier to only write the new rows. Or, well, cheaper, easier in some general sense. This is an example of an incremental query. So instead of doing select star, and this is DBT dialect, instead of just doing select star, you do only select the new events. This gets complicated really, really fast, right? So for a select, it's straightforward. For joins, you have to do a lot more work to figure out what the new rows are, right? You can have multiple joins. You can have aggregations, filters, subqueries. Uh, this is the kind of math for a join, right? This actually, like, on the one hand, this looks a lot more complicated than it is. It's basically saying that you grab the new rows from the one table across the entire other table plus the new rows from the other table across the entire first table. On the other hand, it's like quite a lot of manual work to write all of this out. And it's just something that is much better suited for a compiler to handle. So uh, we thought we would uh, write one because writing compilers is fun. Um, cool. That covers quite a lot of the different directions that we're going in. Some of the stuff that we talked about is in production, some of the stuff is in beta, some of the stuff is still under development. Um, but the stuff that is in production is working, is saving people tons of money today. If you're stressed about Snowflake costs, reach out. Uh, we can use our models to tell you upfront how much we're going to save. Like I said earlier, this only takes metadata, and you can get set up in 10 minutes. Like your bill could be cut in half this week. Um, it's Wednesday, so yeah, that's still true.
Hmm.
If you're
Hmm.
watching this on a Friday, it's more of a next week sort of thing. Um, yeah. Thank you for listening. I'm Ben at Espresso.AI. Um, if you reach out to me, I'll get back to you, or someone on our sales team will get back to you. Um, and yeah, we can go pretty quickly and hopefully help out with cost overruns. Yeah, happy to take more questions.
And one of the things you didn't go over is what is your pricing model?
Yes. I was trying not to. That is a very important question. I'm trying my best not to just make this a pitch.
No, I'm just saying.
So yeah, no, it's a good question. We charge back a percentage of savings.
Oh, okay.
So
Fair
we
enough.
actually just made our pricing public. So we charge back. There's a lot of ML that goes on under the hood. We charge back 40% to be able to cover all of that, or a bit less if you want to pay up front. But we are trying to. Usually, we're talking to people who are trying to cut costs. So this has been a good pricing model to talk through with finance, because every dollar you're putting in, you're getting back 250. It's 150% guaranteed ROI. And finance folks tend to like that quite a bit.
So
Keeps it
if
nice and
someone,
simple for them.
yeah, so
Yeah,
if someone saves 50%, you take 40% of that, or if they take
yeah.
70%, you take 40. Oh, okay. Okay.
No, I mean, so regardless of how much we save you, we will take 40% of the savings. So if we're saving you
Oh, I
a
see.
100 grand a year, we'll charge 40,000.
Okay, I see. Pretty simple. I think that's all the questions I can think of for now. I appreciate the technical discussion. I
Yeah.
love.
Thank you. Hopefully this was fun.
Hmm.
I do have one question.
Yeah.
So you mentioned that, right now, like users, any error that comes up, they immediately think that it's because of espresso, the thing that's running. So right now, like how are you trying to tackle that problem? Like how are you trying to handle user errors or um
Troubleshooting.
no, like more
Yeah.
like their responses, like immediate responses. How are you able to handle that?
Yeah. I mean, we just put everyone in Slack usually. Everyone also, like, oftentimes people just email me, which that obviously is not scalable as we grow, but emailing your rep is always going to work. Feel like most people usually have their rep's phone number. by the time the deal is closed. We have a corporate number as well. So yeah, we just try to get back to people as soon as possible. Realistically, we will the most common thing that people reach out with is, oh, I had a bug the same day that I turned you on. And then just statistically, half the time that happens, the bug happened before we turned on. It was just on the same day. So that's really easy because then we can be like, so it's 3 hours before we did anything. So like we're not that good. Like it's just this
Mm-hmm.
is a different problem. Otherwise, like we'll just debug whatever it is for them. At least enough to be like, look, clearly this isn't us. You can also shut us off. We have a control plane in our dashboard. So if something's urgent, or in general, like people will shut us off if they're debugging something just to not have a bunch of noise in the logs. But yeah, just customer support.
Yeah, I think one of the things I was impressed with when I talked with you and when we were out at the recent Snowflake Summit conference was that you mentioned that you partner very closely with your customers. So you get to know their workloads, you get to know them. There's a lot of dialogue and communication between their customer account executives. So, I appreciated hearing that you even can talk with them just overall about performance with them, not just specifically what your tool does.
Yeah, we do for sure. It's one is it's just always helpful to know what people are up to, what different problems are, and those conversations. I mean, one is it's just interesting. Two is those conversations, also inform what we build and what product directions we take and that sort of thing. We've seen a lot of people be interested in iceberg offloading, for example. So uh, that's something we can facilitate through the proxy. So we're starting to talk to a couple of design partners about, hey, would you use this if we built it? But also just yeah, I think it's very if we can be a resource for people, we're always happy to do that.
Super.
Cool.
Okay, well, let's go ahead and wrap it up for this evening. Thank you, Ben, for being here. This was great information. We'll get the word out. And if anyone can't get a hold of somebody at Espresso.AI, then get a hold of me first, and I know how to get a hold of you and put my emails up to the top of your screen there.
That's
So
right.
it's one of the
All right.
data superhero secrets. So
Thank you
mhm.
very much for having me. This was fun. Thank you all for listening, and yeah,
We'll see you around.
nice to meet
Yeah.
you. Yeah,
Yep,
see you
thanks a
around.
lot. Good
Thanks,
night.
man.